Pleased to announce and introduce our final seminar speaker for this semester, Kim Boddy, who's visiting us from University of Texas in Austin. Kim did her undergrad in physics at MIT and then obtained her PhD at Caltech, also in physics under the supervision of Sean Carroll. She then did postdocs in Hawaii and in Johns Hopkins before arriving at her current position at the University of Texas in Austin. Kim primarily focuses on searching and understanding the fundamental nature of dark matter through a variety of avenues and approaches, including the CMB, large-scale structure, galaxy populations, and properties of dark matter halos. Having said that, today she's going to tell us a little bit about her, and I'm using her words, her side hustle on pulsar timing arrays and the stochastic gravitational wave background, and in particular, how those enable us to test GR and probe for the presence of certain exotic types of dark matter. So I'll hand it over to you. We'll try to keep a little bit of time at the end for Q&A, but the floor is yours.
Perfect. Thank you so much. Thank you for having me here. Thank you for coming at the last seminar. So, right. So as you know, I'm going to talk about searching for new types of physics with pulsar timing arrays. The new physics will be in the particular form of modified GR and these exotic models of dark matter. But to start things off, let me just mention that this whole endeavor of direct detection of gravitational waves got started with GW 150914, right? And so this is well known. People here have surely heard of this, and we have the LIGO, Hanford, and Livingston sites seeing the first direct detection of gravitational waves, which was announced on February 11th, 2016. And so the reason why I point this out is because this date happened to be the date that I gave my previous seminar at IAS. So it's been a while since I gave a seminar here, and my seminar was very that had low attendance, let's just say. There people were occupied with other things, rightfully so. But hopefully LIGO hasn't announced anything this morning, right?
What was the topic?
What was the topic? It was atomic dark matter. And yeah, the phenomenology that goes along with that. But yeah, so at any rate, so now I'm talking about gravitational waves, so LIGO can't undercut me, right? All right, so so they did this, and now it's sort of it's a whole production. They have a ton of events, and this is already 3 years out of date. And so this is these are showing all of the single solar mass to hundreds of solar mass black holes that have resulted in binary mergers, and so they see these different events. But there are also, I have to include the chirp signal. So these are individual binary events that they can go, they have waveforms for, they can go and fit. There is a different type of detection of gravitational waves that are relevant, and that's if you have an entire population of unresolved sources that are giving some sort of background of gravitational waves. And in that case, you're not looking for a single waveform that will tell you the properties of this source. You're essentially hearing what nanograv people like to call a symphony of gravitational waves. It's not just, and there is some red noise that's playing. So that's what the equivalent is of the chirp signal, is just a low noise, low frequency red noise sound. So this is going to be the focus of my talk, is this stochastic background that consists of multiple many sources that are contributing, right? And so at the frequency regime that I'm interested in, this is very low frequency, and it is presumed to come from the mergers of supermassive black holes. And so these black holes reside at the center of galaxies. And when galaxies merge, we're able to potentially get supermassive black hole binary systems that produce this a very low frequency signature. All right, so we have this gravitational wave spectrum. Many of you are probably very familiar with this plot, but here we're plotting the gravitational wave frequency on the x-axis, the characteristic strain on the y-axis. So LIGO is up here at the higher frequencies for the smaller binaries. And nanograv and other pulsar timing array experiments that I'll talk about later are down here in the nanohertz frequency regime, where your supermassive black hole binaries are expected to reside, and Lisa will probe somewhere in the middle. So as I mentioned, the stochastic background is going to arise from large sources of unresolved binaries. And they're stochastic, they're unrelated processes to one another. And you can characterize the characteristic strain by some amplitude times a power law of the frequency, right? So this is a very common parameterization. So as a benchmark point, alpha, this power is -2/3. That corresponds to gravitational waves being emitted from circular binaries, and that's the main energy loss mechanism. You can also talk about it in a slightly different context, this frequency power spectrum for pulsar timing array signatures. And so we'll see this -2/3 or this -13/3 a little bit later on. But this is the landscape of which we're talking about. Okay, so the outline of my talk is that I'll discuss the nanohertz gravitational wave detection that pulsar timing array experiments have performed, and sort of have a broad overview of what goes behind this observation. And then I'll talk about signatures of modifications of general relativity in various ways, and how this affects the observations that we do. And then I'll briefly talk about signatures of ultralight dark matter. Okay, so here you go. The pulsar timing array experiments are numerous. So in North America, we have nanograv, and nanograv consists of these various telescopes. We have CHIME since the loss of Arecibo. The Europeans have a set of telescopes. The PPTA in Australia. So those three are sort of the main three that have existed for on the scale of decade plus. More recently is the Indian pulsar timing array experiment that often joins up with the Europeans. Much more recently, there's Meerkat, and there's also the FAST telescope in China. So with the exception of China, the rest of these experiments, I believe Meerkat's part of this, form the International Pulsar Timing Array. And the only reason China is not involved is political on their end. So but we certainly have colleagues in the CPTA who we discuss things with. So this is the International Pulsar Timing Array. There are multiple experiments that are going after the same thing, using different observations of different systems. And so what we observe are millisecond pulsars. So we have to have high precision timing of these objects. And of course, as the beams from the pulsar spin and pass our line of sight, we see them as pulses. And so I figured I'd show this since NSF went to such trouble to make such a nice animation. So millisecond pulsars. Right. So in summary, the data that we have from nanograv, and I'm going to be very sort of biased here in terms of what I show, since I'm a part of nanograv, I will focus on this since I know it the best. But we have 15 years of data that we included in the most recent release. It consists of 68 pulsars, And so this is the timing data. So on the x-axis, it's just a different pulsar. So you can see as pulsars have been added to the data sets, starting from 2005 and moving forward. And so this is, you can see that not all the pulsars are timed always. And new pulsars are constantly being added to the observations.
What do colors mean?
The colors actually indicate which instrument observed it.
So the green line stopping, that's a reciprocal collapsing, I suppose.
Probably, yeah. All right, yes. And so obviously each of these data points means something. We're talking about the timing of pulsars. And so what exactly do we mean by this? Oh, let me make a shout out to the rest of the teams that have participated in this. So we have INPTA and EPTA, Parks and CPTA, along with Danagrav, made this announcement in June of last year that we all have reported some level of evidence for a stochastic gravitational wave background. Sorry, I sort of buried the lead there because I felt that most people would be familiar with this. But we have this whole host of papers that have been associated with that. Much more recently, as in the past month, we also have recent results from Meerkat, but I can't show you any of them because this is, if you try to search for it and look at the paper, this is what you get. So eventually they will have their paper posted. I'm not sure what the holdup is. The acceptance date was last month. So I'm not sure what Monthly Notices is doing, but they're doing something. And so let me not comment on this. Maybe I can comment offline, but officially this hasn't been released yet, so I won't talk about insider information. Okay, so how the actual measurement goes is that the observable is our timing residual. So we take some observed arrival time of our pulse. Of course, this is integrated because we don't see an individual pulse from the pulsar. We have to stack pulses in order to get a good signal to noise. But we have the observed arrival time sort of over an integrated period. And then we have some model, right, for the predicted arrival time. And so this is going to depend on a number of things, what the pulsar spin period is, but also their spin down to the pulsar. So the pulsar is not perfectly stable and spinning exactly at the same period. So we have to pay attention to its derivative. It matters where it is in the sky, its proper motion, because this all gives shifts to the arrival time, how far away it is from Earth. These sorts of things go into our timing model.
So how does the proper motion affect that? Because you need acceleration to.
Yeah, so for the fact that we are moving in
So is the
the
acceleration of the Earth mainly?
or even the pulsar could be in some system. We have binary systems of pulsars that we observe.
There is also Shklovsky effect where you have, if you have a proper motion, if the pulsar has a proper motion, then you have a p dot associated with that.
So when you take the baseline model, you subtract it from the observed arrival time, you get this leftover piece that we have to deal with. If we didn't model everything quite perfectly, there's some sort of unmodeled process that we still have to deal with. And then we have noise, right? And so this noise comes from intrinsic noise to the pulsar. There's measurement white noise, and then the actual pulse has to propagate from the pulsar to us. And so in the interstellar medium, there's a whole bunch of things that affect that propagation. And so there's some frequency dependent dispersion that's happening. So this all has to be dealt with and modeled as noise. And then any sort of gravitational wave that comes and alters, say, our position on Earth, is going to give a contribution that looks like red. So if we have something that we expect, for instance, so these are the blue lines that we would expect to be exactly at some constant pulsar period. What we actually observe are the red blips, and so there's a little bit of offset to those blips. So the timing residual is essentially capturing that offset. And so we need to know, and we need to time these pulsars at the level of microseconds. And so this is one particular pulsar observed over a number of years that show you the residual and how well we need to time these things. Okay. So that's the measurement, and once again, this animation is mostly to give you context as to where these pulsars are in the galaxy. So this is its distribution if you're looking at it, at the galaxy from one angle, but then there's a nice like three-dimensional movie that was made to kind of give you a sense. So it's obviously not spanning the entire galaxy, it's only a portion of the galaxy, but this is the pulsar timing array, the array of these pulsars distributed across these scales.
And none of them are in globular clusters, right?
None of
Some
them.
of them are.
Yeah, I think there are. Yeah, there are globular clusters. Some of our pulsars are quite close to one another. Well, not, I mean, it kind of depends on your different definition of close, but there are pulsars that are somewhat close to one another.
Because for those, the acceleration effects would be quite substantial.
Yeah. So the pulsars, I think in the data set that I showed, though I'm not 100% sure, I'd have to remind myself and look it up, but we did throw a pulsar out the window in terms of our data set that we released with the 15-year data, because it was just, we couldn't control the noise properties. Okay. So a little bit of math. Now that I showed you all the pretty pictures, I'm going to take you through some of the math. So we have our source of gravitational waves. It's going to induce a metric perturbation. And so a way that you can phrase the observed quantity is thinking about the fractional shift in the arrival time of these pulses. And so this is the delta t, the period over the period. And it involves taking a projection along the line of sight to the pulsar and taking that projection of the metric perturbation itself, okay? And then you integrate along the path of that the pulse takes. So this theoretically is what we're looking for. The most, I wouldn't say natural, but the most common thing to do is to take a plane wave expansion for this metric perturbation and to characterize the amplitude under this particular decomposition. I work with something slightly different. I work with total angular momentum waves, in which I decompose things according to spherical harmonics, since we're essentially working with a spherical sky. And so, they're different basis expansions. They're going to give you the same thing. The calculations look slightly different, but I'm going to show you some of the TAM wave.
So what's alpha?
Oh, yes. So alpha is different possible polarizations,
Okay.
which will play slightly later. But for the time being, I'm just thinking about transverse traceless modes. So we have metric perturbations, and so with the plane wave expansion, if you plug everything in above, you would see that there's a term in which the metric perturbation matters on Earth. And this pulsar term is very oscillatory, and so it averages to 0, and so this pulsar term is dropped. So we're working basically with thinking about perturbations that happen at Earth, and thus affecting all of the pulsars that we see. So the in terms of TAM waves, it's something slightly more complicated. There's a lot more math at the beginning, which ends up making things look nicer at the end. So all the nastiness here comes at the beginning, all the nastiness up here comes from having to deal with the pulsar channel. But the nice thing is that I can describe my my timing residual essentially as having some amplitude times some angular response here that I labeled S of L, and these are in the basis functions of spherical harmonics. So that's what we're dealing with. And the benefit of TAM, as I said before, is that we have observations on a spherical sky because our pulsars can be taken to be sort of infinitely far away. So we have a stochastic gravitational wave background in which we assume that there are going to be nice homogeneity and isotropy arguments that we can make for the correlation between these two different amplitudes. And our angular correlation function we can write down, or we can write down an equivalent power spectrum for it, right? And so to be clear, this is the angular correlation function of timing of pulsar pairs, right? So we're still looking at what is essentially equivalent to the monopole of, say, like the CMB, right? We're not looking at any anisotropies here. So this angular correlation function between pulsar pairs or the equivalent power spectrum is what we're going to deal with. And so in sort of the way that I frame things, in the TAM formalism, this F sub L squared is going to contain all of the angular information. All right.
What was W of that?
Oh, it's some presumed window function of the observations. And so, oh, yes, thank you. The nice thing about this, in either case, regardless about which basis function that you choose, you always find something that is very nice at the end of the day when you take the pulsars to be infinitely far away, is that the angular information completely decouples from any sort of frequency information. So we can write it as a product of the two and talk about them independently, at least theoretically. So for transverse traceless modes, we have a very, very nice looking expression for the power spectrum. The corresponding angular correlation function looks like this. And so as of a handful of years ago, this plot is showing you as a function of angle, right? This, okay, so right, this is supposed to be theta, and showing you what the correlation function looks like. And so this orange curve is this function here. And so HD stands for Hellings-Downs, the two people who wrote the paper that first derived this. And then there was some, in this IPTA data, there was some offset that was giving rise to a monopole. But this is what the data looked like, and there was no evidence at this time, which was in 2022, for any sort of angular correlation, right? So there are two different parts. We need the angular correlations that follow this HD curve, because that's theoretically what we would expect from gravitational waves. That tells us that what we're seeing are gravitational waves and are not some other source of noise. Right. And then we also have the frequency power spectrum bit, which also gives us other information. So this is where we were as of a couple of years ago, and at least for nanograv, this is the latest result that gave rise to claiming evidence for detection. And so we have the frequency power spectrum, we have a red noise feature, and these violin plots are showing you how we essentially decompose our timing data into harmonics in frequency space. And so this fundamental frequency at the lowest value represents 1 divided by 15 years, which is the longest observation time of any pulsar that we have. And then these are harmonics, so integer multiples of that. But we had already seen some weird noise, red noise feature that was unexplained in data before. Multiple experiments had seen this before, but the problem is that there was no evidence for this angular correlation up until summer of last year. So this is what really is carrying all of the important information that says it's a gravitational wave. Okay, so this is the result. That's great. Now let's actually move on to the latter parts of my talk where I'm going to start modifying things. And so I want to think about signatures that are beyond general relativity. My main line of work is not thinking about theories of modified gravity. I want to do this in the most agnostic way possible. And so the way that I do this is I say, well, I'm just going to insist that the various degrees of freedom that can exist for my metric perturbation are actually physically realized. And so I can have my standard transverse traceless modes, which are the plus and cross polarizations. But let me also say that I can have my two different vector modes, as well as two scalar modes. So this is the breathing mode or some longitudinal mode that is in the direction of propagation. So I can just insist that these particular polarizations do exist, and I don't associate this with any particular model. Any particular model would, sort of tell you how much power there is in these different things. But I'm just interested to know what the angular correlations look like under these modifications.
These exist in non-Einstein, right? The vector and the scalar.
That's right. That's right. So all of these would be beyond GR in some way. But the scalar modes are easily realized in some scalar tensor theory. The vector modes are a little bit harder to get. But but in principle, you could think about writing some new theory down and getting this. So we can compute detector response functions, these Fs that I was talking to you about earlier. And for all of our different modes, we get very, in principle, simple expressions. So the tensor mode is what I showed you before. But once again, we have scalar and vector modes that are easily derivable. So instead of showing you the equations for them, let me just show you what they look like.
So do you need to have quadruple moment to excite the vector and scalar modes?
So the vector and scalar modes, I'll show you in the next slide, actually. The vector and scalar modes, the vector mode can have a dipole contribution, and then the scalar mode can start having a monopole. Everything has a quadruple. But yeah, so that will be important later, just a couple minutes. Yeah. But this is how things look. So this is the Hellings-Downs curve. These are our standard tensor modes. You can have a vector mode, which seems to blow up as you get to smaller and smaller angular separations, but really is normalized by having a finite distance to the pulsar. And then I'm showing you the scalar transverse mode that looks a little bit more boring. And then the scalar longitudinal mode is divergent and also needs to, in the infinite pulsar distant limit, it needs to be regulated in some way. So yeah, and looking at how things behave at small angular separations or at finite distances is the subject of the paper that I swear is going to appear soon. This is my fault. So yeah, as soon as my class takes its final and I grade it, then I can get back to finishing this. So I'll have more to say on that later.
Is there any reason why vector polarization behave differently from both scalar and tensor at small angular separations?
So the scalar longitudinal mode, which is not even plotted here, also exhibits problems as well. Is there a good intuitive reason why the vector mode does that? So not intuitive. Not intuitive, at least for me. It does certainly fall out from the math of it, but
Yeah, but is it the vector mode or is it calculated as vector mode or longitudinal?
I'm sorry.
Is the weird behavior due to it being a vector mode or just that it's a longitudinal?
Oh, it's due to it being a vector mode.
So for scalar longitudinal.
Yeah, scalar longitudinal it simply has a problem overall, because the scalar longitudinal mode, that makes sense, because the gravitational wave is surfing. And so there's a divergence and so it scales approximately logarithmically with the distance of the pulsar. But why the vector mode ends up having this problem at small angular separations is something that's not exactly intuitive to me. I usually don't think about vectors. Scalar perturbations are very easy to think about. I don't have a good explanation for the vector. Okay, so in terms of power spectra, and here I'm also allowing the velocity of the gravitational wave to be different from 1. But if you want to focus for the time being on just the darkest, the black curves, this is what you get. This is what the Hellings and Downs curve looks like for the tensor modes. And for the vector modes, you see that you get this contribution down here for a multipole 1. So you have a dipole contribution, and both the scalar longitudinal and in principle the scalar transverse mode have a scalar contribution, monopole contribution.
So considering low speeds here would be justified, like not in contrast with the velocity because it's a different frequency.
Because it's a much lower frequency. That's right. So in principle, and people have written down potential ways to get this. Like I said, my specialty is not thinking about theories of modifications of gravity. But it is something that is reasonable and consistent with LIGO. I don't think the velocities are going to be quite that low. But this is, I just wanted to demonstrate.
So there are models where the velocity is 0.4 at nanohertz and 1 at kilohertz.
Yeah. So there's other physics that can take place at lower frequencies, and by the time you get to the higher frequencies, some mechanism happens. It's been a while since I've actually read that paper, but yes, that is the justification for it. Right, and so all of these curves are normalized because everything here depends on the frequency power spectrum for the gravitational wave, right? That sets essentially the amplitude of my correlation functions and therefore my power spectra. So all of these are normalized so that the quadrupole is at 1. But this is to emphasize, the drastically different behavior, especially in terms as you get to higher and higher multipoles of what the ratio of the quadrupole to the octupole to the hexadecapole should be. So, right. And so this sort of leads me, and you can also mimic, right? This is a very fake way of trying to mimic things because these curves are all normalized individually and depends on how much a vector mode is going to contribute in a given theory compared to the tensor mode. But this is just to say that, you can have something that looks like a Hellings-Downs curve, but it's not actually a tensor mode, right? It just looks like it. So, but essentially the important difference between the tensor and the vector mode is that there's a dipole contribution that vector can contribute. And so this led to my colleagues and I to think about some new approach to dealing with the analysis of the correlation function for PTAs. And so what PTA collaborations currently do is they all assume that the angular correlations are given by standard GR, which is a perfectly fine and reasonable assumption to begin with. And so they just insist on this. So there's a Bayesian analysis that is done to actually process the data. But once that data is processed, they go and ask, is there a correlated red noise process in all of our different pulsars? And then they use frequentist statistics. They use the frequentist estimator to actually tell us what the significance of the correlations looking like Helling's Downs, what that correlation is. And so that is what is reported by PTA collaborations when they say we have 3 sigma, 4 sigma evidence for Helling's Downs. So they use this mixture of Bayesian and frequentist statistics. And then, of course, they're assuming the Helling's Downs curve is dominantly quadrupolar, but certainly there's no process to isolate that quadrupolar signature since they're just assuming the HD curve. And so, so what I wanted to do instead was to create a more model independent approach and just ask, can the data tell us what the different contributions in the power spectrum, in the angular power spectrum, what they look like, right? So we should see a dominant quadrupole, and then we should see higher order multipoles with smaller amplitudes. And so if we do that, we can use Bayesian statistics throughout to actually analyze the data instead of, and we don't rely on the HD curve. That said, we allow all of these parameters here. So here's the signal, how it's modeled. We allowed the amplitude of the gravitational wave, at least in this initial study, to vary. For the purposes of this particular paper, we fixed this minus 13/3 that I mentioned much earlier in my talk. And here would normally be where we would put the Helling's Downs information, the angular information. But instead of that, I'm decomposing this into Legendre polynomials and just asking what is the contribution of the quadrupole, the et cetera, et cetera. And then we also model our red noise as well, that is coming from each individual pulsar itself. So that's a source of noise. And then we also have to model white noise as well. Yeah.
Yeah. Can I ask a little more about the statistics complaint? I mean, it would seem to me that if you're trying to calculate evidence, you're in a very Bayesian mode.
Yeah.
Do you really mean that they're trying to calculate a Bayesian evidence, but using a frequentist approach? How does one even do that?
They have a what is called a multi-component optimal statistic. And they so the details of this, I think maybe we can sit down together and open up their paper. But yes, they are definitely talking about evidence over just a red noise, a common red noise process that has zero correlation. Right, that doesn't have any HD correlation with it. And they use that information to report their sigma. Yeah, so that
Fascinating.
maybe we can talk after this. But that's what's currently done. And there's been a lot of work behind establishing what that optimal statistic should be. But nonetheless, I come from a much more cosmology background where I like to do my analyses in a single nice framework. But in order to do that, at least in the way that their data analysis pipeline is set up, doing this decomposition into Legendre polynomials by far seem to be the best route to go, at least for the time being. So, right, so we can do this.
So will the vector and the scalar modes also lead to a minus 13/3 dependence in the power spectrum?
Oh, so this power spectrum is dealt with just saying that the energy loss of a circular binary system has this frequency dependence. So this has nothing to do with the actual
Wouldn't they be different because dipole radiation, quadrupole radiation, they have the different powers of V over C.
No,
Those
that's
are
right.
different powers of frequency.
No, you're
So
right. You're
in
right.
reality, they would all have different powers. If you just do some simple radiation for the binary.
Yes, that's correct. Yes. So the 13 thirds was fixed here because we're gonna inject a normal gravitational wave. And we're gonna search for a normal gravitational wave. At least for this this setup, because this is the most analogous thing to what is currently done.
So that implicitly assumes that your radiation is predominantly quadratic. And the
Yes.
dipole and monopole contributions are net, so insignificant.
Yes.
And it's more than that, right? Not just quadrupolar, but like it needs to be from binary specifically.
Yeah, yes,
Yeah.
yes, absolutely. So the
Could you give a reference for where they do this frequentist way? Just because their papers say that they do it in a Bayesian way and that they quote Bayes factors.
yes,
So could you point me to the paper where they actually go through that data is fundamentally? They don't put, high squares per degree of freedom.
No.
They don't do that. So what's?
that's right. No, because the vast majority of the analysis is Bayesian. Right?
Yeah.
But in order to calculate the evidence of HD, they take their post-process Bayesian analysis and then do this optimal statistic on top of it to actually come up with that significance factor. Any of the detection papers do this, and I can show you where. And so the results of this mock study that we did was, saying if you had some really idealized situation where you had a low level of noise, of instrument noise, what you would get if you had 50 pulsars observed over 10 years, and then we went up to 150 pulsars that were observed over 30 years, and showing how well you could reconstruct the different multipoles, given that I injected just a normal Hellingsdowns curve. And so the injected values are showing that theoretical value for HD. And this is what we're able to reconstruct. So definitely the quadrupole here, but with this sort of lower statistics information, we kind of don't see L equals 3, and certainly nothing above there. But if you go and observe for longer with more pulsars, you start tightening these error bars. And so you start having a hope of being able to see with some future setup, being able to see not only the quadrupole, but also L equals 3, 4, possibly, maybe 5. And so all of this information is very helpful when deciding if maybe as sort of the first check to see, do you have any deviations from GR? Because the ratio of these quantities has a certain value when you are thinking about transverse traceless modes, and they have different values for different setups. Here, we didn't even fit the monopole or dipole contribution, but you would presumably want to do that as well for once again potential evidence beyond GR. And so we can take these curves and sort of give you the reconstruction of what it looks like in angle space. So here, 50 pulsars, 10 years gives you something that kind of oscillates a little bit around the exact predicted value. And then you get something that's much tighter as you move on. So this was just a mock study where we simulated these various pulsars. Of course, now we have data. And so we can ask, what do the data say? And the data have a strong evidence for the existence of a quadrupole, for this C2 value, but nothing beyond. And I'll show that in actually the next slide. But here we do allow, we do a proper analysis where we allow the power of the index of the power law for our frequency power spectrum to vary as well as our amplitude. And so this is sort of the reconstruction that you get from the spline. Yes, that's right. The spline is what you get sort of using the optimal statistic way of doing things, which also has a handful of caveats that I can maybe talk offline about. And then using the Legendre reconstruction of our analysis. So we have evidence for a quadrupole, and and that was evident when analyzing also the 12.5 year and going to the 15 year, right? So the 12.5 year, this is the 1D posterior for C2. It was consistent with 0, and now we have a very nice essentially measurement of C2, and C3 is still not measured. But things are getting better, and with future data sets, hopefully we can resolve.
The dashed line is the predicted value for the ups and downs, the hello.
Right here?
Yeah.
Yeah. So this is what it looked like with the 12.5 analysis of where, there's large deviations, and so there wasn't really that much evidence, but then with the 15 year, things got much tighter. Okay. Right, and so I have some backup slides. I can talk more about looking for C0 and C1, but they have a handful of complications that I don't want to get into, but I'm happy to discuss offline. But in principle, this is a way, especially if we can get C3 and the higher multifolds, as once again being the baseline indication of how consistent things are to GR. It's not perfect, but at least it can tell us if something is drastically off, certainly.
What is the predicted value of C3 and GR compared to C2?
The dashed line is not.
C2 and C3.
Not that small compared to
Yeah, you can also see it.
1 order of magnitude.
Yeah, you can also see it here. So here versus here. And then, of course, like I said, we'd want to do monopole and dipole, which we did do in our nanograph paper. But in the interest of time, I do want to say something about signatures of ultralight dark matter. And I put this in because we do have a paper, Nanograph has a paper about searches of signals from new physics, but these are all sources that are, some exotic new physics sources that's happening in the early universe. And while I'm interested in this isn't my primary science. And so every time I give a nanograph talk, I obviously focus on this, and I never get to talk about the thing that I actually did, which is the ultralight dark matter part of the new physics paper. So I'm just jumping right to it, skipping all the early universe stuff. So the idea with ultralight dark matter is that if dark matter is, say, a scalar field, the scalar field is going to be very, very light, or can be very, very light, to the point that the occupation number of the scalar field is very high. And so the way to actually model this is as a classical wave, rather than, individual quantum particles. So this wave, at least in our galaxy, would oscillate in some coherent manner. And the coherent length, coherence length is given, in this particular simulation that my colleague Jeff Dror did, by this value L, and the oscillations occur at a frequency that is dependent on the mass of the particle, right? And so if we're sitting here at Earth, I believe he's plotting the density perturbations that you would expect from this scalar field. And so
So is the coherence length comparable to the de Broglie wavelength of the particle, or?
Yeah, so yes, that's right. Right, so it's the relevant coherence. So now you have to start thinking about, the size of your galaxy, the size of substructure that you expect dark matter to make. And so let me cut straight to the punchline. this cannot be all of the dark matter. If you are in the range in which the pulsar timing arrays are sensitive to. It is way, way too light to be all of the dark matter, but that's not to say it can't be a fraction. Okay, and so we have various things that we can do. We can also, so that's just the gravitational aspect of it. You could also imagine coupling this scalar field to the standard model in this way. And so this is some effective theory with the cutoff scale lambda, and you can imagine coupling this phi in some dilatonic way to E&M, to SU3, to the different masses of leptons and quarks. And so we have gravitational coupling only, and coupling to the standard model that can affect things in various ways. You can accelerate the pulsar. You can have spin fluctuations because it causes particle mass fluctuations. So you change the moment of inertia of the pulsar as it spins. We time pulsars against atomic clocks, and so you can have this scalar dark matter that is messing with your atomic clocks. There's also a birefringence effect that came out very, very recently from EPTA, but I haven't had time to read that paper. And so these are the results that you can get. Over here on the left is the gravitational coupling only, and at least nanograv is not really constraining things down at the level that we really need it to, which is below the local dark matter density, right? I've told you that this thing cannot be all of the dark matter, or else it washes out substructure that we see. So, you know, things are improving for depending on what type of analysis that you do, but we can get really nice constraints from this dilatonic-like coupling for certain types of coupling that can be that are certainly comparable to atomic clock experiments, but are also in regions of parameter space where atomic clocks, those experiments don't have anything to say.
So sorry, the density that is constrained on the big plot there
Yes,
is
that's right.
the local density.
That's right.
So we're only sensitive to up to some distance.
Yeah, because we need the metric fluctuations to be influencing us,
Right.
and the pulsars, which are not that much farther
So
away.
even say denser regions of the halos don't actually matter.
That's right. To some approximation. And so Jeff and I are working on an improved treatment, because there are two different lines here. If you're interested, I can go into it, but we're working on some improved treatment where we don't have to make two essentially limiting assumptions. But the real answer is going to fall somewhere in between.
And what's the 2s+1 factor?
Is the degrees of freedom. So if you have, depending on if you are talking about a vector particle, so that
So the factor is 1 for scalar.
for scalar dark matter, this is, S is 0.
Yeah.
Okay, and so upcoming prospects, we are combining our data with the IPTA. And this is showing the overlap in terms of the number of pulsars that the major PTA experiments have observed. And this was their, it wasn't a data combination, but it was a data comparison run through the same analysis pipeline, showing that all of these 3/4 main pulsar timing array experiments essentially agree that we are seeing consistent results in terms of having a gravitational wave. And, you know, there's SKA that's coming up, but in terms of the US, the deep synoptic array, people are pushing for that, which would be in North America. So yes, so that's just the beginning. So this is the end of my talk. I wasn't paying attention to the fact that that clock is wrong. But we have this new window that can tell us about the nature of gravity, can tell us interesting things about astrophysics that people here in the audience have been thinking very in depth about. and maybe early universe cosmology, but there's still plenty of work left to do. I'd like to advertise the fact that I'm one of the organizers for an Aspen summer workshop called Physics in the Era of nHz Gravitational Waves. So I've sent some of you an email about this. I will follow that up once the applications actually open. But when they do open, it will be at the end of next month that they are due. So I will just leave you with this XKCD comic, and I'm happy to take any questions.
We have time for a couple of questions, so.
There were plenty throughout as well.
We can, in that case, head over to lunch, but I do want to advertise that Kim is here today and tomorrow. Basically, you can find a schedule with Udip's announcement email. We also have maybe a couple of slots left for dinner tonight, so if you would like to, this is your chance to get your name in there. I think we'll be going to local Greek around 6, so just to keep everybody in the loop on that. But besides that, yes, find the sign up sheet and Udip's email. Grab her time. She'll be here till tomorrow evening, so we have all of today.
Oh, yeah, that's right. And if you want to talk to me about dark matter, or cosmology and structure formation, also happy to do that.
So, well, thanks again.